welcome to this video in the equilibrium chapter. Today we're going to explore qualitative and quantitative entropy. So before we start, please have handy your companion worksheet, your plan sheet, and of course, we're going to be doing some calculations, so you will need your calculator. Without any further ado, let's get started. So when I think about entropy, I think about the room on the left. That is not what my room looked like growing up, because my mother would have had my head, but we would say that there is a high degree of entropy in this system that is right here. It is quite unlike the same room on the right, which looks like a lot of work had to get put in order to actually organize the room. This could have been one of those hoarders that you guys see on TV, where everything is just everywhere and it's a holy mess. But anyway, what we have here is a high degree of entropy, and on the right we have a low degree of entropy. So entropy, which is represented by a capital S, means a degree of disorder, or how disorderly a system is. Randomness, chaos, all different ways that people can talk about entropy. And the way you can really think of it is, the greater the degree of disorder in a system, the higher the entropy will be. Now, nature, for instance, is always going to favor maximum entropy without even having to do anything. And really, take this example that's here. Let's get a better picture of that. Where you have a closed system, you have the blue atoms that are over here, the red atoms that are over here. And the minute that we open the system, these two groups of atoms are going to mix. So we are going from two more orderly systems to a giant disorderly system. You can think of it sort of like this. At one point, I watched some crazy documentary on National Geographic about, like, what if humans just simply left the Earth? Well, when we say nature favors maximum entropy, this is really what we're talking about. A cityscape like this would only happen, like, I don't know, 10 or so years after humans left, because no one is there to put the work in to actually clean it up. It requires a lot of work to take entropy and restore order. So in terms of the chemistry, let's start looking at qualitative entropy changes and determine if the entropy will increase or decrease when looking at a reaction or some system process. Of course, we have our two thinking monkeys here, so get your thinking caps on and let's go. Our first example is how phase changes will alter and affect entropy. So here we have a cube of ice that is melting. Do you guys think the entropy will increase or decrease as the ice melts? Well, if you said the entropy is increasing as ice is melting, you would be 100% correct. Part of what you need to think about is what's happening at a particle level. On the particle level, a solid cube of ice is an orderly crystalline lattice, as we see here on the left. Whereas when energy is put in and ice melts, the crystalline lattice turns into now the particle model of a liquid, where the particles are more on top of one another and are undulating and are a mess. So anytime we have a phase change from solid to liquid, the liquid has more disorder than the solid does. The same can be said of our gases. Gases will have the most entropy in any system. Why? Because you guys know gases spread out, take the shape of the container, intermingle. There is more disorder in a gas than there is in a liquid, and certainly more than there was in a solid. So moving along from physical changes, now we're going to look into how chemical changes will actually alter entropy as well. And here is a single replacement reaction that we are looking at, where we have a solid A reacting with a liquid BC, making liquid AB and C, which is a gas. Do you guys think the entropy of the system is going to increase or decrease? Well, if you said the entropy is increasing, you would indeed be correct. You guys will notice here that your products are liquids and gases, whereas your reactants are solids and liquids. And as we know from our last slide, liquids and gases have more entropy than solids and liquids do. So it is important to take into consideration what you are making in these chemical reactions and what their phases are. So our third example here features this reaction, and what you're seeing is what's called the electrolysis of water, where the electricity that is stored in the battery is being used to drive a chemical reaction, which is separating the water into its component elements that make it up. So the question is, all right, this is what you got. Is the entropy of this system increasing or decreasing? Well, if you said the entropy was again increasing, You would indeed be correct. So why is that happening? Well, in the last two examples we did, we were looking at solids, liquids, and gases, and yet here they are all gases. So we can't use phase to delineate whether our entropy of the system is increasing or decreasing. We have to do something else. And what we have to do is we have to consider how many reactants we have versus products. And here I have two molecules of water that are being decomposed into two hydrogens and one oxygen. That gives me a total of 3 products on the right versus 2 reactants on the left. So the takeaway from this slide is when you have things that are in the same phase and your reactions form more products than they had reactants, there's always an increase in entropy. So simply count the coefficients on the left side and compare them to the coefficients on the right. The side that has more is the side where entropy is increasing. Fourth example we want to talk about is what happens when you alter the temperature of a system. So throwback to the 80s, there was a movie called Short Circuit. This was the robot that was in there. It was Johnny 5, and Johnny has some Starbucks coffee at 40 degrees. He heats it to 80 in his microwave. What happens to the entropy of the coffee? Well, once again, if you said the entropy increases, you would indeed be correct. And what happens is very simple. The hotter something is, the higher the average kinetic energy is, and the more random the motion of the particles are. So anytime your temperature is going up, the entropy of the system is increasing. Anytime temperature goes down, the entropy of the system is decreasing. So our fifth example is dissolving. Let's say we are going to dissolve some solid sodium chloride and hydrate the ions. During solvation, does the entropy increase or decrease in the system? I see a trend here. Once again, the entropy is indeed increasing. So why is it increasing? Well, what you have to consider is that when you have a solid, liquid, or gas that is now dissolved in water, you are taking what was once a pure substance and you are introducing water into it. So you're going from, let's say in this case, sodium chloride, which is a solid, and now you have aqueous sodium chloride, where that means you have the sodium chloride plus the water. So there are now 2 different substances that are in there. So the randomness of the solution is much greater than the randomness of the pure substance. So aqueous solutions will always have more entropy than their pure substance counterparts. So at this point, let's pause the video and let's try some. Here are 5 questions. I want you guys to tell me, is the entropy going to be increasing, decreasing, or will you be unable to tell? So pause the video now and then unpause it when you're ready for the answers. Okay, so if you did this correctly, you should have gotten these answers. I want to call your attention to E. E was a toughie because we were looking at a reaction where we had reactants and products all in the gas state. So that meant we had to count the number of moles on each side. And we notice we have 1 and 1, which is 2, and we have 2 here. So what gives? Hard to tell. Well, that's a case where you actually have to rely on a quantitative entropy calculation, and that is what we are going to jump into in the last part of our video here. So quantitative entropy change is calculated using the entropy values for your reactants and your products, and we use this formula, and it's very simple. It looks like this. The change in entropy is equal to the entropy of the products minus the entropy of the reactant. So delta S equals S prod minus S react. And you'll notice that that does look a lot like your delta H or your delta T calculation, where we are simply taking the values of the products and taking away the values of the reactants. So you might be wondering, what does this positive delta S value mean? Well, a positive delta S value means that the entropy is increasing over the course of the chemical reaction. So the system is becoming more disorderly, chaotic, and random. You also might be wondering where we get the entropy values that we're going to plug into that calculation. Well, if we look here at the table on the right, this is an excerpt from a thermodynamics reference table, which is found in the back of your AP Chem book. Here is a large view of that, and you'll see on this, it's listed alphabetically, and there are enthalpies and free energy values. And of course, here is the column we're interested in. This is the entropy value for whatever the substance is that you are looking for. So we have to figure out, is it a solid, is it a liquid, is it a gas, and then we take the entropy value and use it accordingly. So let's try our first example. Here we have the synthesis of sulfur trioxide, and let's see if we can qualitatively figure out what's happening in entropy. I'm looking at my reactants and products. I see that everything's a gas, so I can't use that in order to determine whether entropy is going up or down. So I'm now seeing how many moles are on the left versus the right, and it looks like I got 3 moles of reactants, 2 here and 1 there, and I have 2 moles of product. So my guess is that the entropy of this system is going to go down. So I should get a negative number. So let's now verify it quantitatively. I know that in order to calculate the change in entropy, I've got to take the entropy of my products and subtract the entropy of the reactants. Before you start, there is one consideration that you have to pay attention to. Like Hess's law of heat summation when we did it, you are getting values here for the entropy just like we did for the enthalpy. And these values have to get multiplied by the coefficients that are part of the balanced equation. So if we were using the entropy value of sulfur dioxide that's here, we would have to multiply this 248.1 joules per Kelvin by 2. So pause the video now, try and set the problem up, and see what you get for your entropy value. Unpause when you are ready for the answers. All right, if you did this one correctly, you should have gotten a change in entropy of negative 188.3 joules per Kelvin, which means the entropy of the system was decreasing. And that was pretty much as we thought that it would. We eyeballed it and we said entropy is probably going to go down, and quantitatively our value now corroborates that. Let's try another problem. Pause the video now, set up your entropy equation, and let's get an entropy value for this reaction. Let's try another example of an entropy calculation. And the only thing I want to call your attention to here is the fact that you are given a coefficient which is a half. So you're going to take the oxygen and you're going to multiply it by this. It's actually going to be half of what it normally is. So yes, even though you're not supposed to balance equations with halves or anything, occasionally you can see that written in an equation like this. So pause the video now, try and set up your problem, and see if you get an answer. Okay, if you did this correctly, we should get an entropy that goes down again. It is negative 93.09 joules per Kelvin. You guys think you're ready for one more? Let's try this last equation here. It's the decomposition of hydrogen peroxide. Pause the video now and see if you get an answer that's correct. Praise be to God. Looks like we finally got a reaction where our entropy of the system is indeed increasing. We get 125.7 joules per Kelvin. So pretty much, guys, those are our entropy calculations. So for homework, I want you to try these 4 equations. They are in your plan sheet. Let's see which one of these gives you the greatest increase in entropy. So I would like you to calculate all of them and make an assessment. So that's pretty much it for me. I assume if you guys have burning questions, we can certainly bring them up and talk about them in the burning questions segment tomorrow. It's been a pleasure to be with you guys, and I will catch you on the flip side. Peace out.
That's all, folks.